Hello, in this tutorial, I'm going to introduce the blockMesh meshing utility for OpenFOAM, and I'm going to do this tutorial using OpenFOAM v2412. Okay, so let me jump out of this and jump over to my Windows, and I'm going to launch my Ubuntu. So I'm going to pick up from a previous tutorial where we looked at the lid-driven cavity flow. So first thing I'm going to do is I'm going to load OpenFOAM 2412 just by typing this command. And then I'm going to go to my run directory. And from the last time I had a cavity case. So I'm going to make another copy of cavity from the tutorials as we did before. And you can see my commands I'm typing over on the right-hand side here. So foam tutorials, incompressible tab, ICO, foam tab, cavity. If I tab now, I can see what's inside the case. There's a couple of different versions. So if I just copy cavity, but I already have a cavity directory here, so I'm going to call it cavity new mesh. So now that copies it, if I ls, I can see I have cavity and cavity new mesh. And as before, if you find it more convenient, you can open Windows Explorer with the explorer.exe. So I've just copied the original cavity from the tutorial, and this cavity was from the last tutorial we ran. Okay, so if I go inside my cavity new mesh and I run blockMesh. So if you remember, blockMesh reads from this blockMesh dict file in the system folder. So in this tutorial, we're going to go through how that's constructed, and we're going to change some things about it to give you an understanding of how it works. So if I just run blockMesh, it creates the default mesh. And now if I go touch case.foam, and then explore exe dot, and I'm going to open up this case in Parview so we can see it. So just to remind you what the mesh looks like, if I press apply, and I have surface edges here, and you can just see that you have 20 cells by 20 cells in this block. So if I go back to my terminal, the first thing I'm going to do now is I'm going to open up the blockMesh dict in Emacs. So we're going to go through the different settings, and then we're going to change some of them to see what they mean. So at the very top, we have this entry called scale, and in other versions of OpenFOAM, it might be called convert to meters. So essentially, when we give the coordinates of points, uh, they just all get multiplied by this value. So it's just a global scaling factor. And so it's mostly just for convenience. For example, if you know the coordinates in millimeters, but you want to create the mesh actually in meters, then you will put 0.001 here to scale everything down. So the way meshes are created in blockMesh are any geometry or mesh that can be composed of multiple blocks, where a block has 6 faces, like a hexahedra. And it only creates structured meshes, essentially structured hexahedral meshes. So this is one of the simplest cases because it's just one block. So here we're given the 8 coordinates. So these are the coordinates that define the corners of the block here. So we have 0, 0 down here. You can check this, for example, if we go to sources or filters, even, and you search for, let's say, a sphere. And at 0, 0, we create a sphere. But this is a really large sphere, so let's just make it a little smaller. You can see this is the 0, 0 point. And so if we go back to our terminal, that's the first point. The next point is 1, 0, 0. Going back to power view and updating the center to be 1, 0, 0 and apply. You can see that it's moved over 0.1. It moves over to this point here. And the reason it's 0.1 is because that 1, 0, 0 here is just scaled by 0.1. So the actual coordinate is 0.100. So you can check these points are defining the 8 points of that block. Then when we come to this, the definition of the block, which you can have multiple blocks, it says hex because they're all going to be hexahedral cells. And then you give the list of the 8 vertices that you've defined above here that make up that block. And that's what these are. So 0 here, if I go up here, I'll put comments. So this is the 0th vertex, or let's say vertex 0. This is just a comment. This is vertex 1, vertex 2, etc., etc. So go down to vertex 7. So you can see it's 0 vertex. This block is made from vertices 0, 1, 2, 3, 4, 5, 6, 7. And then the 20 by 20 is the number of cells in the X direction and the Y direction, and it's the local X direction for the block, which we'll learn more about. And then this grading refers to are the cells getting bigger or larger. So in Abacus, it would call it biasing. Okay, so then let's see the effect of changing some of these settings. So for example, if I look at the top left corner, so this vertex 3 would be the top left corner. So if I go back to my presentation here on the second slide, these are how the block was created in this case. So they gave the 0th, 1st, 2nd, 3rd, and because OpenFOAM for 2D meshes, it actually has to make a 3D mesh with at least one, or with one cell exactly thick. And then we 4, 5, 6, 7. So this is the ordering that is being used. So if we look at vertex 3 and 7, and maybe we're going to move those a little bit in the, let's say, minus X direction. So we have to move them the same because the front and back plane has to be the same for a 2D simulation, otherwise we get errors. So if we go back here, instead of saying 0.1, maybe we can go minus 0.1 in the X direction. And then we can also do that for the 7th vertex as well. So this will be vertex 7. So now I want to rerun blockMesh to recreate the mesh so I can see the effect of my changes. So I could just save this blockMesh dict, close it and then run blockMesh. But then if I want to go edit it again, I have to reopen this. So it's often convenient to have a second tab. So up the top here, you can just go Ubuntu 24 is the one I'm using, and you can just see it's adding a second tab up here. I'm not sure it defaults to Ubuntu colors for some reason when you open it this way. So if I load OpenFOAM again in this one, 2412, I type run, you can see I'm in the running directory. See I have cavity new mesh. I'll go inside here, and that's where I am. So I'll just run blockMesh, and I will go back to power view. I'll delete my sphere, I don't need it anymore. And then here I'll click refresh, and then if I skip back to the start time, you'll see that it updated the coordinates. So if I rotate this back around the correct way, so I actually just moved these 2 points up in the corner back in the left direction. So you can see, okay, you can easily change these coordinates. That makes sense. And if we go back to our first tab, so let's look at some other changes we might make. So we have 20 cells by 20 cells, so obviously we could change it to 40 by 20. So if we try that, go back to this tab, run blockMesh again, go back to our power view. You can see now I have 40 in the X direction and 20 in the Y direction. I'll make it both 40 by 40. Go over here to my second tab, rerun blockMesh. I'm skipping back over here. So you can see now I have 40 by 40, so 4 times as many cells. So that's the number of cells in each direction. The next thing we'll look at is just this grading over here, just one by one. So in C++, even though this isn't just an input file for C++, it doesn't care about lines. So you can spread things across multiple lines if it's easier for you to read. I'm going to do that here for these settings, just to make it easier when I look at a different grading option. So these numbers here represent, in this case, the first one represents in the X direction, the ratio of the last cell to the first cell, the ratio of their sizes. So if I set this to 5, that means that in the X direction, the cell on the far right will be 5 times bigger than the first one. So it'll still be 40 cells in that direction. It's just changing the bias essentially. So if I jump back over here, refresh, skip back, you can see that the cells over here now are 5 times the size of the cells over there. And you could do the same thing in the Y direction, for example, as well. But oftentimes we're interested maybe if we flow over different objects or walls, we often want to have smaller cells near the walls. So for example, in this cavity case, we probably want to have small cells near the walls themselves because of the boundary layers rather than in the center. So it would be convenient if we could define grading towards the walls. So if we have a single grading factor across the block, we can't do that. So we essentially need in the X direction multiple grading factors. And to do that in OpenFOAM, we can use what's known as multi-grading. Yeah, so instead of 5 here, I can actually use brackets or parentheses. And then within these parentheses, I can define a series of other sub-parentheses. And in those, I'm going to put numbers, which are going to define how I'm going to split up the x direction into different regions of grading. So inside one of these brackets, I will put the first number, which is between 0 and 1, represents the percentage of geometry in the x direction I'm talking about. So if I say 0.2, it means the first 20% in the x direction. So I'm going to split it up in 3. So I'm going to have a 0.2 percentage geometry, then 0.6, and then 0.2 again. So the first 20% of geometry, I'm going to set one grading, the next 60%, like the middle section, a different grading, and then the last 20%, another grading. So I'm going to grade towards the wall at the left, then have maybe uniform in the center, and then grade towards the wall at the right. So the first thing is the percentage of the geometry, but then we've said 40 cells. Now we need to tell it the percentage of the cells that will go in. So I'm going to put, just as an example, 30% of the cells there, and I will put 40% in the center, and then another 30% at the far wall. So the first number in each of these sections, and it doesn't have to be 3, I can split it into many sub-regions as I want, will be the percentage of the geometry and then the percentage of the cells of your 40 cells. And then the last thing, the last number of the 3 numbers will be the grading. So that, like in the simple grading, that's the ratio of the last cell size to the first cell size. So at the left wall, I want a positive number because I want small cells to get, and then cells to get bigger. In the center, I want the ratio just to be 1. I want them all uniform. And then at the far side, I want it to be less than 1. So I want the first cell to be larger than the last cell. So 1/4, so say 0.25. So I've only done this in the x direction here. And then the y direction, I'm just using simple grading. So if I save that, and I come over here in blockMesh, and then I go back here and go refresh and scale, or go back to the start time. So you can kind of see here that the first section of our geometry is maybe from here to here, and you have small cells coming up to large cells, and then the center 60%, they're just all uniform, and then the last 20%, I think they're grading down again. So obviously I selected numbers to give a nice smooth transition, just not to have a big step jump in the cell size. So you can see in that way in the x direction now, we can capture small cells on the left and small cells on the right. And then in the center, they're just more uniform. So if I'm happy with that, I could do something similar in the y direction. So if I just copy and paste and do exactly the same thing in the y direction, and then just to note in Emacs how I did that. So if you want to copy and paste, so first you set a mark, so holding Control, press space, so you can see maybe the keys I was pressing, and then if I press up or down, then it'll start highlighting, because setting a mark is like start of highlighting. So if I highlight the first line and then I go escape, let go W. So that was an escape key I pressed. That's copied it, and then holding Control, press Y. So Control Y is to paste. So yeah, Emacs commands are a bit strange if you're used to traditional Windows ones, but once you learn a few of them, they can be pretty convenient. Okay, we'll save that. Go back to blockMesh. Come back here again. So now the X and Y direction, I've done the scaling. So you can see now I have nice small cells on the top wall, right wall, bottom wall, left wall. So in terms of if we've been expecting boundary layers, maybe that's a more efficient distribution of cells. Right, so the next thing we want to do is go a little bit further down. So we have this edges. So it's just blank, this edges entry. So edges allow us in between any of these vertices on the block, instead of having a straight line, which is the default, we can have a curved line, or we can have a spline, or some more exotic features. So what we're going to do is from the bottom of the domain, so from 0 to 1 and 4 to 5, they have to mirror each other, we'll maybe put a negative arc, or an arc curving down. So to do that, the syntax is I'll go arc from vertex 0 to vertex 1, and then I will give it, to define an arc, like an arc of a curve, I have to give a third coordinate. So it's going to fit an arc between vertex 0 and 1, and then some coordinate. So I'll just pick a coordinate in the center, so 0.5, 0, 0, that would be the very bottom. That would just make a straight line. But I'll just push this down to be maybe minus 0.1, just to push the center point down. And I will do the same thing with vertex 4 and 5, like here. Generally, if you're making something, this is trivial in this case, the geometry, but if you're making something with blockMesh, and you can make some complex geometry with blockMesh, you normally need to sketch a diagram like this. It just makes your life much easier for tracking which vertex is which. And then the front points, I just need to change this to be 0.1, so the Z coordinate is moved forward from 4 to 5. So if I rerun blockMesh, go back here, refresh, skip. So you can see now it's these bottom two edges are now curved. So you could do the same thing with all the edges, or you can even have splines where you give lists of points and you can go all sorts of complex curves and shapes. Great. So then one of the last things to look at in the blockMesh dict is down the bottom we have this boundary. So this is where the patches are defined, and the patches, which are regions of the boundary where we want to apply a boundary condition, are defined using this syntax. So we just give a name, which we can make up. So we have moving wall, fixed wall, and front and back. And then these faces, they are describing the faces on the outside of these blocks. So 3762. So if we go here, you can see 3762 defines this top moving wall. So there is a convention for the direction that's defined. So it's the right-hand rule. So you can start at any one of these 4 vertices. And then if you use your right hand with your fingers curled, which are thumb pointing out of the geometry, so outward facing normal, then you just go in the directions of your curved fingers. So if I picked 2, I would go 2, 3, 7, 6, or 3, 7, 6, 2, or 6, 2, 3, 7. So as long as you're going in that same direction with your thumb pointing outwards, all of those are valid. But if you go the other way, then blockMesh will complain that you have an inside-out face. So that's how that moving wall is defined. But what I want to do now is these 3 sides, this side, the bottom, and the left, so the right, the bottom, and the left, they're all just one patch called fixed walls. So I'm going to change the right wall to be a new patch because I want to give a different boundary condition on the right wall. So you can see here that's 2, 6, 5, and 1 are the vertices. So 2, 6, 5, and 1. So I'm going to make a copy of fixed walls. And I'm going to give it a new name called moving wall 2. And I'm going to remove the other faces. So 2, 6, 5, 1 is just the right hand side, and I just need to make sure I remove it from the fixed wall. So fixed wall will just be the left and the bottom now, and moving wall 2 will be just the right, and moving wall will be the top. So if I save that, rerun blockMesh, and I go back to PowerView, and I skip, nothing happens because the mesh looks the same. It's just changing the boundary patches. The only difference is you'll see here that it's picked up the extra patch. So by default, the internal mesh is shown, but it can actually look at the individual patches. So fixed walls are these two, and moving wall will be the top one, and moving wall 2 is this right one, and then you can even view the front and back as well if you want. So that looks all the same. And you can pick them by different patch types as well. Okay, so yeah, that's essentially like all the different options you might consider in blockMesh. So the next step we're going to do is we're going to actually run the simulation. But we are missing something. So we add a new boundary patch called moving wall 2. So if you remember inside our 0 directory, we've given the boundary conditions for velocity and pressure, but we haven't mentioned this moving wall 2. So if we were to try start IcoFoam now, it will say you're missing definitions for those. So you'll see here it says cannot find patch field entry moving wall 2 inside 0p boundary field. So it's saying inside a 0 folder, inside a p file, and inside the boundary field section, it expected to find an entry for moving wall 2, but you haven't given us to it. So let's add those entries now. So I'll go with p first. So I'll just copy the moving wall settings. So I'll call moving wall 2. So a normal wall condition is just a 0 gradient condition for pressure. And then I'll open U, and I'll copy U, copy the whole thing. So moving wall 2. So instead of a fixed velocity extraction, I want to have a rotating flow similar to the original cavity. So I'll just go negative y direction. So on the right hand side, it's basically like pushing straight down and then it's pushing it across. So it's going to cause a rotation. Very good. So now we're ready to go. So if I run it now, icofoam, it may work, but it'll likely explode. And by explode, what I mean is the current number is likely going to be much greater than one, and it'll cause it'll become unstable and it'll produce unreasonable results. So initially we had 20 by 20 cells that were uniform, but then we have now gone to 40 by 40, so they're at least half the size. So that means for the same physics problem, um, we initially had a max current number of close to one, so now we'll probably end up being greater than one. So this piezo algorithm that icofoam uses will be probably unstable. Also, we graded the cells towards the walls, so we probably have much smaller cells than the original case. So we can try this. We can try icofoam and see what happens. So, okay, it seems to be stuck now, so I'm just going to hold Control and press C to kill the program. So if you see what happens, it starts and the max current number jumps greater than one. And remembering the current number of one means that the flow is traveling one cell, whatever the smallest cell, one cell per time step. And that's kind of the stability limit for this piezo algorithm. And you can see it starts to increase. It goes to 8, then it goes to 81, and then it goes to 597, and then it kind of gets stuck. And eventually it will go, you'll probably see NaN, which is not a number, and it'll just give up. So as you refine the mesh, you'll need to reduce the time step if you're using the piezo algorithm, which is used by icofoam. So let's make the delta T 10 times smaller, and maybe we don't need to run to the same time, so I'll make that 10 times smaller, the final end time as well. So if we run this now, you can see that the current numbers are a little bit smaller, but they're still too large. Oh, I accidentally pressed something there. So if I will reduce the current number again, or reduce the time steps again aggressively, say 100 times, and I run icofoam on it. Let me just check I don't have any time steps yet. And I might actually set the sides back to be flat as well. Okay, we're okay this time, are we? Yeah, okay. So this is running and our current number is much, much smaller. So that's actually fine in this case. So you want it to be sometimes, depending on if the mesh is kind of skewed as well, even being close to one could make it be unstable. All right, so if we check now, ls, we have lots of time steps printed out. So if we go back to PowerView, we'll refresh, and I'll actually tick off skip 0 time because I want to see the 0 time. So I'll skip back to here and I look at the velocity field, but I'm going to also turn on the cell to point interpolated data so I can see the values of the boundary. So you can kind of see it's a value of 1 here in the x direction, 1 here in the y direction. So if you looked at the x and the y components and then the magnitude, you can see those. I'm going to line it up in this direction and then just set it to 2D just so it'll keep the projection in that direction. And then if I skip to the end, maybe, yeah, you can see that's the at 0.05 seconds what the velocity magnitude field looks like. So if I play in time, you can see it's developing. So in this case, it's probably informative if I add some streamlines. So if I add some streamlines, and probably I don't need how many it's going to suggest. Maybe it will reduce that. So 20 is probably fine. So there's our streamlines. I will turn off this line. And let's see any other settings we want to change here. Okay. Yeah, so if I color those by velocity and I then play it, you can see, let me jump back to the start time. So if I play it, you see these streamlines, a small vortex starts in the top corner and then it starts to kind of move or propagate outwards. And like in previous cases, you could turn this back on and maybe you could show the pressure field at the same time and maybe change the opacity. If I can scroll down here, maybe to something small, 0.1 is fine. So now you can see both of these things at the same time, and then you could use for the streamlines, you could also maybe use tubes to visualize these as well. So in this case, you can see it developing, and you might even start getting a small vortex over here rotating in the opposite direction. And then if I go to this original one, maybe I'll make a slice in the Z direction. And so just a slice. And if I look at the pressure, so you can see with a negative pressure in that top corner as the fluid's being sucked away from that point. Previously, we had a peak in the top corner here, but now it's been transferred to the bottom corner here where you're getting the fluids all being squashed, basically. So yeah, that's everything we're going to show here. So that shows you the basic structure of a block mesh stick and how to change the things and what they mean. So that's the end of this tutorial.